Okay, so in this lecture, we will talk a little bit about neutrino mass measurements. There will be a kind of overview. Maybe in some subsequent lecture, we might go into details of one or two of these methods. But before I do that, let me just recall some history. Namely, you all remember that the neutrino was proposed by Pauli in 1930 as a desperate solution to the uh, continuous energy spectrum of the betas coming out from beta decay, and other things also we'll come to in the subsequent slides. The problem of angular momentum conservation, of spin statistics, and so on. The other thing that was we have also seen is that the cross section for detection of these neutrinos is very tiny. It's about 18 orders of magnitude smaller than typical interaction cross sections of nuclei. And so this was the work of Piles and Bethe, which is basically a kind of dimensional argument, a beautiful illustration of how powerful dimensional arguments can be. In the same year, Fermi published his paper in Zeitphysik on the theory of beta decay. And it was modeled on the theory for electromagnetic interactions, the quantum theory for electromagnetic interactions, which was a current form, and the same he took over for beta decay as well. Then we come to the proposal for detection of neutrino, a radiochemical detector, which was done by Pontecorvo in 1946, but the experiment was not carried out till much later. And then the first real-time detection of neutrinos was done by Reines and Cohen, first in 1953, but the final result was published in Science in 1956. Okay, so again, just to recall, the energy spectrum of electrons in beta decay is not discrete, and this is a big surprise because the initial and final states were supposed to be definite. Quantum states, but the energy spectrum was continuum. It is a continuous spectrum, as is depicted here. It rises and then falls. It should have been something like this, but it was not. And so, in the case of, let's say, carbon 14, what is expected was it goes to 14 nitrogen plus a beta. That would be two-body decay, and you should see this discrete spectrum. On the other hand, if you have a third particle, which is what is the proposal of Pauli, then you have three-body decay, and then you can have a continuous spectrum as depicted by this curve here. Now, there is also a problem of violation of angular momentum. We know that the angular momentum is conserved in all processes, and so if carbon 14, which is a spin 0 object, this is also an integer spin object, then how can it emit a beta particle which has a half spin? Because by that time it was realized that electron and beta minus is the same, and that the electron has a half spin. So also there is a problem of parity that we'll see, because if, for instance, this is carrying away L equal to 1, but then the parity is wrong. So this is positive parity here, and then that can take away L equal to 1, but then that has to be negative parity. So there is a problem of this sort as well. And as I said, angular momentum as well, because you can't have 0 going to 1 plus half plus whatever L may be, 0, 1, 2, whatever. But you have this odd, this half integer spin here, and you can't reconcile this. Then there is also the problem of statistics, because these are integral spins, so they obey Bose-Einstein statistics. Beta obeys Fermi-Dirac statistics. So there is a problem on the statistics front as well. So in order to solve this, unwillingly, Pauli proposed this particle. He said something that cannot be detected, but ultimately it was detected, and he was right. So initially, Reines explored the possibility of detecting neutrinos from a nuclear bomb. I think this also I might have said before. But however, you don't explode bombs every day, and so it's difficult to. The only advantage of doing it via a nuclear bomb was that, of course, all the neutrinos would come in a very short span of time, within a fraction of a second, and of course there will be later maybe activities produced, but they would contribute much less. So in any case, you would be making neutrinos in a very short span of time. However, it can't be repeated. So Louis Alvarez suggested that he use a reactor as a source, because then you can repeat the experiment. And the same comment was also made by Enrico Fermi. Reynes and Cohen and colleagues carried out these experiments in Hanford. They got the first sort of signals, positive signals from Hanford, and then they went to a higher power reactor, the Savannah reactor, and by 1956 they had firmed up the signal which was due to the anti-neutrino, and they published their result. Earlier to that, Pontecorvo had suggested detection of the neutrino through the inverse beta decay process. That means a new neutrino comes in, it interacts with chlorine 37, produces a beta minus and 37 argon. And 37 argon actually gets, it decays with a half-life of about 34 days by electron capture. And so this can be separated out from this huge mass which has chlorine 37. So it can be some organic fluid like C2Cl4, CCl4, etc. And then you separate out argon. It's a rare gas, so you can bubble in, let's say, dry argon in that, and then it takes away the radioactive argon, and you can count that separately. I think this probably should be argon, if I'm not mistaken. So this can be used to measure, but of course this is a offline method. This is not a real-time method, because you have to let's say irradiate maybe at a reactor with some source for the number of days corresponding to about a month, and then you separate out this argon and they again count for a month. Meanwhile, of course, the rest of the detector can be again exposed to the whatever source you have. So at that time, the sources that were thought of was the nuclear reactor and the sun. Now, this idea was actually taken forward by Ray Davis, who was at Brookhaven at that time, and he and Bacall made the proposal of building such a detector and for solar neutrinos. But Davis actually carried out this experiment first at a reactor, and there he showed that he didn't get any signal. So the conclusion was that, of course, this detects electron type of neutrinos, whereas of course it was not known that there are other varieties of neutrinos. So at least neutrinos versus antineutrinos. So the neutrino is what you detect here, and so he didn't find evidence for that. So he concluded that the reactor actually produced antineutrinos. Now, fast forward to the more or less the present day. This is a summary from the particle data group in 2006. So they keep, of course, summarizing the data that exists, and there's a 2024, 2025 data, but this is taken from an earlier version. So in that we know, from that we know that the spin of the neutrino is half. The electric charge, if it exists at all, is between 10 to the minus 4 to 10 to the minus 15 times the electronic charge. So essentially we have no evidence that it is charged. It is a neutral object as far as we know. If it has a magnetic dipole moment, then that magnetic dipole moment, the magnitude of that is 10 orders of magnitude smaller than the Bohr magnetar corresponding to the electron. So the electron magnetic moment is measured in terms of the Bohr magneton, and this is 10 orders of magnitude smaller, if at all, non-zero. The mean life by the mass is of the order of 300 seconds by eV from a reactor experiment. From solar neutrino experiments, it is of the order of 7 10 to the 9 seconds per eV. The number of neutrinos, flavors, as I said, we will come to that. There are 3 flavors of neutrinos, and all 3 have been detected, and in fact, even their mass bounds exist now. So the number of neutrino flavors from the Z0 resonance profile comes out to be 2.994 plus minus 0.012. So it is 3 to within the accuracy of the experiment, which is basically like 1 part in 2000. So it's a part per mil kind of accuracy, to better than that, in fact. The again, a summary of the upper bounds on the masses is that the electron neutrino mass bound is this was taken in 2006. We'll see that this has improved in the meanwhile. So at that time, it was about 2.2 electron volt by c squared. The mass bound on the muon type of neutrino is about 190 keV by c squared, and the tau uh, about 18.2. These mass bounds have not changed substantially, but this one has improved by almost a factor of 4 to 5, as we shall see. Okay, so for any of these neutrino experiments, of course, you require a source of neutrinos, and this is a list of the sources of neutrinos. Of course, what is used in the neutrino measurements, the neutrino, especially the mass measurement that we'll talk about here, but this is useful when we discuss other kinds of experiments as well. So, if you were to classify these sources, then these are about half a dozen sources. One is the atmospheric neutrino source. This comes about because cosmic rays interact with the upper atmosphere, producing pi plus, mu plus, and they in turn decay to mu plus. But you also produce kaons in smaller numbers. They also decay to muons and to first pions and then muons, and then these decay to produce roughly 2 nu mu's for every nu e, and the energies are of the order of GeV. So it's a power law spectrum, and the neutrino flux is of the order of about 10,000 per meter square per second. We also get neutrinos from the sun, and they are of the order of about 610 to the 10 per meter square per second. I hope this number is right. I'll check that out. Anyway, in any case, we'll be talking about other kinds of experiments as well later. So anyway, I'll check this number out. And the energy of these neutrinos range from about 100 keV to 15 MeV. Man-made sources such as nuclear power reactors, the energies range from about 0.1 to 5 MeV. The flux at about a kilometer is about 10 to the 13 per meter square per second per gigawatt thermal. Okay, gigawatt thermal, remember this. And power reactors are of the order of 1 to 3 gigawatt thermal. In fact, now the latest reactors go all the way up to 1.6 gigawatt electrical, which means about 5 gigawatt thermal. Accelerators for with proton beams of the order of 200 GeV or less, they also produce neutrinos. By the way, the LHC now, of course, can produce neutrinos with beams of the order of 7 TeV. So those energies would range from up to about a TeV or so. And the fluxes are of the order of 10 to the 9 per meter square per second at a kilometer. Of course, when you go to distances of the order of 10 to the 3 kilometers, then they go down by a factor of 10 to the 6, so you have only about 1,000 per meter square per second. There are geoneutrinos because in the Earth's crust you have uranium and thorium, and also you have some amount of potassium 40 all over the Earth, including probably the core or the mantle and things like that. And they actually contribute to 40% of heat production inside the Earth. Of course, we get much more energy raining down on us from the sun, but if you were to talk about energy produced in the Earth through radioactive decay, then these geoneutrinos have, actually this should be of the order of 4 MeV, I think. Of the order of 4 MeV, 4.5 MeV maximum, and the flux is of the order of about 610 to the 6 per meter square per second. Supernovas, of course, they occur in our galaxy probably once in 50 years or so, or near the near environments of our Milky Way, and so they are quite rare. We got to detect supernova neutrinos from an event that occurred in 1987A, that's called supernova SN 1987A. And they, as I said already in the last lecture, they release about 99% of their energy as neutrinos. And this number is very large, the order of 10 to the 60, and this ranges over a few seconds. Okay. Finally, there is the all-pervading Big Bang cosmic neutrino background, which is about 330 per centimeter cubed, just like the 2.7K microwave background, which exists all over. That is about 450 or so per centimeter cubed. So this is a reasonable fraction of that, but we have evidence for the 2.7K microwave background. In fact, very precise spectra have been measured, and it follows the black body radiation and so on, and many measurements have been done by looking at it very precisely. However, we have not yet detected the Big Bang cosmic neutrinos. There are proposals to do that, but we don't yet have a detection of these Big Bang cosmic neutrinos. Okay, so now let's come to how do you weigh the neutrino, direct measurements of the mass of the neutrino. So as I already talked about in the last lecture, from the energy spectrum of low Q value beta decays, and especially you measure the spectrum near the end point, you can get good bounds on the neutrino mass, and if it is finite, we might even be able to measure it. And so the best case that has been used hitherto is the tritium case, that has an endpoint of 18.6. But there are other cases like rhenium-187 where the endpoint is even smaller. However, to measure these directly is difficult. So there are cryogenic bolometers where you have 187 rhenium impregnated, and that has been done, but the bounds are much less precise as compared to tritium. But there is hope that maybe one day we'll be able to get a strong source of 187 rhenium, put it in a bolometer, cryogenic bolometer, and maybe we'll be able to measure this. For muon and tau type of neutrinos, you make basically energy momentum measurements in two-body decay. So in the case of the muon neutrino, the pion, which let's say the pi plus, stops, and then it emits the neutrino and the muon. And so if you precisely measure the energy momentum of the muon, you can infer the mass of the neutrino from there. And this has been done. Similarly, in the case of the tau neutrino, you look at decays of the tau lepton, and you can look at 3 or 5 body decays and then infer about the mass of the neutrino associated with the tau, the new tau. So the most precise measurements on, or precise bounds on the electron neutrino mass have been made by the so-called Katrine experiment, which are improvements of the earlier measurements at Troysk in Russia and Mainz in Germany. So that makes use of the idea that you can make a electromagnetic spectrometer. So you have a solenoid which focuses the electrons from the tritium, then they are retarded to a potential of about 18 keV or so. So only those electrons near the end point which have energies greater than 18 keV or so. Of course, you can tune that with this voltage, and you can of course transport these using this solenoidal device, which is of a very special character, such that you can have almost parallel electron transport, but also very good transmission efficiency, and that transmission is of the order of 30-40% or so. And then you have a set of detectors which measure these electrons. Okay, so you can, using silicon detectors, you can have a very precise measurement of the energies of these electrons and close to the end point. So the momentum follows these magnetic field lines. This is the red line shows that, and for more details, of course, you could go to the paper that is There's a Journal of Instrumentation paper. It has all the details in its whole, you know, as a whole. You can see what that does. And the energy resolution is given by this is about sub electron volt. Okay, so for masses which are larger than this is very good. For masses smaller than this, of course, then you have to use a resolution function and see the sensitivity of this. So from their simulation, they were able to show that if the electron neutrino has a mass greater than 0.2 electron volt by c squared, they will be able to see it. Uh, and of course, if it is greater than about zero 0.4 electron volt by c squared, they will be able to measure with some precision the mass. So this is a picture of the Catrine spectrometer. You can see this is a huge setup. You have the molecular tritium source. So it's a windowless gaseous molecular source. You don't want to have any windows which can degrade the energy, but more importantly can spread the energy, because the energy loss is also statistical. So you have to have a windowless, but of course if you have a windowless gas source, tritium gas source, then you have to have very strong pumps which will not allow this radioactivity to go to the further downstream of this pipeline. And also, since it is radioactive with a large half-life, about 12 years or so, then you want to again capture this radioactivity. So the efficiency of capture in these pumps should be close to 100%, and they have achieved that kind of efficiency of capture as well. And then these electrons are transported using a solenoidal kind of spectrometer, and then it is retarded in the main spectrometer and guided onto a detector system. The huge size of this detector can be seen from the fact that the chamber actually had to be very carefully transported between two buildings in a street in Karlsruhe, and this was done in about 2006. Okay, so this is an overview of the Catrine's spectrometer, and you can see that this again the same components are shown, and this again the same things are shown, that you have a setup where you transport these electrons into the spectrometer, and a summary of the measurement is shown here. So the last part of the spectrum, so the rate per pixel in counts per second is shown here. So this is the end point, and you can see that these are the counts clustered here. This is the background beyond the endpoint energy, and if you were to fit this spectrum along with the resolution function and so on, then the bound on the m nu squared, or sorry, the best fit m nu squared is like minus 0.14 plus 0.13 minus 0.15 eV squared. So the best fit value implies that the bound on the m nu is less than 0.45 at about 90% confidence level. This was reported in a seminar at CERN by Catherine Valerius on May 2025. This is the title of the talk. Perhaps by now there might be published results of this, and you can see now that this is a very tight bound on the mass of the neutrino. Of course, it is possible that it may not, this experiment may not see a finite mass, and then there have to be better kind of detection mechanisms, better schemes if you want to go to the 100 millielectron volt or even 10 millielectron volt sensitivity levels. In fact, such things exist, but I won't have time to talk about that here. Okay, so I'll just one slide on the rhenium cryogenic bolometer for measuring the beta spectrum. So you can see this is the FT, this is the Fermi-Curie plot with some number of detectors, and you take the sum spectrum, and if you look at this very carefully, you can put a bound on the upper bound on the mass of the neutrino. So the mass squared bound is about 147 eV squared, and so the mass bound that they extract is like about 22 electron volt by c squared at 90% confidence level. Okay, so the other flavor of neutrino, which is the muon type of neutrino, that, as I said, is measured using the two-body decay of the pion, charged pion, and because of course then you can measure the muon through using magnetic spectrometers and so on. So the momentum of the muon is measured, and this is the expression for the m nu mu squared. This is given by this m pi squared m mu squared minus 2 m pi m mu plus p pi squared. So you have to measure the energy momentum of the muon, and then from there you reconstruct the invariant mass of the muon type of neutrino. So this experiment was done in places where you can get a secondary beams, rather strong secondary beams of pions and hence muons, and this was done at Switzerland, the PSI lab, and the P mu is measured to a precision of about 3.5 ppm, and hence you can get a measure of this m nu squared. So this turns out to be okay. Strange. This bound is not given here, but this is of the order of 190 kilo electron volts or so. (190 kV by c squared). Okay, so this is the bound on the muon neutrino mass. This is the reference given here, the 1996 reference. Perhaps there might be one or two measurements which improve this bound, but this is, in principle, it is not possible, perhaps, to, with the methods at least that we have, to go down to electron volt levels. That would require a very different kind of measurement, if at all. So it is best that we, if this tiny mass be measured through the electron type. Nevertheless, it is useful to see how such bounds can be put for the muon type of neutrino, and in the next slide we will see how the tau type of neutrino. So here you use 3 and 5 body decays. So you plot these things as a function of the energy of the hadron times the momentum, and so you can, again, from simulations you can get a measure of the tau type of neutrino mass as compared to the tau electron, the tau lepton mass, and the collaboration at LEP, which looked at tau lepton production in Z0 decays, that put a bound of about 18 MeV so MeV by c squared at 95% confidence level. So the idea is the same, that you do an energy momentum measurement of all the charged particles that you have at your disposal, and then reconstruct the invariant mass of the neutrino. Okay, so I end with a small cartoon. Namely, it shows a neutrino physicist. He says, I'll be working on the largest and smallest objects in the universe, superclusters, which have multiple galaxies in them, and neutrinos. Neutrinos are the smallest objects that we know of. I'd like you to handle everything in between. So he tells his colleague. Okay. So with this, I just summarize what we have seen. We have recalled a bit of history related to neutrinos. Very briefly, we saw how upper bounds on the effective masses. So it's an effective mass, as we have realized that the leptonic flavors are not the same as the mass eigenstates. So it is an effective mass that you are measuring for the three flavors of each of the three flavors of neutrinos. And we saw how briefly we can arrive at that, at the effective masses, in fact the upper bounds on those masses. Thank you.